Yeah, it looks like it'll be light today. That's all right. I do actually have a lot of stuff to cover, so I might go a little bit fast. So if you have questions, do speak up. I might go fast and then probably end up ending early as a result. But I do want to make sure that we have enough time to get through everything. So, and yeah, I mean, and I abandoned exceptions for STL, and I needn't have bothered since we're not getting to the relevant stuff until today anyway. But yeah, so Friday, April 8th, the last class, hard to believe. Tutorial 10 is due Wednesday. If you're submitting tutorials late, let me know. I don't go back and check. You have to email me or contact me on Discord. I do see some submitted tutorials. I don't know, man. I'm not going to go back and just ad hoc remark everything. So please tell me. But yeah, any questions on the schedule or anything else? I guess the schedule's over now, but
will there be a final review session like we did for the midterm?
Yeah, so probably not in this class. That's so I don't have, I did not prepare a final review session yet. I can answer any questions if we have time at the end of this class. What I was going to do is I will prepare one for the B section because we'll likely have time to go over it, and then I'll email everyone a link and a timestamp for when to start watching. So hopefully that's good enough. Or I mean, if there was enough interest, I could arrange a separate session, but I sort of doubt there'd be enough interest.
Oh, go. But there was 2 TAs that hosted kind of an extracurricular session.
Oh yeah. Oh, for the TAs. Yeah, yeah. There was nothing planned. You know what? I'll contact Lars and see if somebody has some extra hours and they can do that. Yeah, that's not a bad idea.
All right.
Cool. Okay. So yeah, we're gonna finish STL and then we'll go finish exceptions. And yeah, sorry that it's sort of mixed and matched there. Didn't work as well as I thought. So last class we were talking about the STL library, which is a bunch of collection classes and a bunch of algorithms that operate on those collection classes. And then in between those two things, we have some iterators. So those are the things we started looking at. We got as far as lists. So the nice thing about lists, this is and this is the example we did last class. So we have a bunch of students that we defined. I guess probably we don't need that anymore. And then these are student objects, and we made a list of student objects. So this is a doubly linked list, the way it is implemented in C++. So when we push students onto the list, one copy is made, but then it can grow and shrink without having to make a lot of copies of students like the vector does with its backing array. So that is the advantage. If we're storing objects, then linked lists might be a good choice. Although you should benchmark anytime you're using, if efficiency is important, just use benchmarks, because you'd be surprised. Sometimes overhead is incurred where you don't expect it. But okay, so we pushed a bunch of students on, and then we called sort. So the list has a built-in sort function. The vectors do not. We're going to see how to sort vectors using iterators and the algorithms library. But for now, for list, we do get a built-in sort function. And by default, this sort uses the less than operator, right? If I don't have this, I believe it causes problems. Let me see. There it is. Okay, so now I'm trying to call sort, and I'm guessing where I'm in the wrong place. P6. Yeah, so the compiler goes looking for this less than operator, and it cannot find it. So this by default uses the overloaded less than operator. Of course, we can also define our own. So here we've sorted students according to the less than operator. And then we made a separate function called compare that took two student objects. I made it a friend of my student class, and it was able to return a Boolean. Basically, it takes two student arguments and returns a Boolean. And that is if you have that function signature, regardless of the name, then you can pass that in as an argument. And then you can sort the students that way. Yeah, so I guess we'll just quickly take a look. So we sorted the students. The less than, I believe, is alphabetical order. It appears to be alphabetical order. And then the compare function was GPA in order from greatest to least. Camera's blocking. Oh, sorry, really? Is it still blocking the screen? I turned it off. Oh, no, it didn't. Oh, sorry about that. Oh, there we go. Better? Should be better anyway. All right. The other thing, you can make a global function that's a friend of your class. The other thing you can do is make a static function. So that's what I did here. I called it comp, and it has to have a different name, but it still takes two student references and returns a Boolean. And then in that, I sorted according to student number. All right, so then the nice thing about making a static function is that it doesn't have to be a friend. I have access to the private member variables. And then to pass that in, I would say use the scope resolution operator or an object, and I could pass it in that way. So sorted according to comp. So student numbers. Okay, so we can see, yeah, these are in numerical order according to student numbers now. Okay, so that's the ways that we can call the sort function on the linked list or the list class. So questions on that? Okay, so we don't get random access on this. And yeah, copying our own objects works as long as we have the stream insertion operation. So I don't even know what I meant to say there, but I'm going to skip it. I'm not going to spend a lot of time on that. You can only sort if you have the comparison operator less than, or if you supply some function that compares two of your objects. The next thing we'll look at is double-ended queues. We're going to go over this quite quickly, but essentially it is a fancy version of a vector that grows at both ends. I tried to look up exactly how they implemented it, and it was actually quite complicated. So there's chunks of data, but you also get, so it's like a combination of a doubly linked list, and each node holds an array, I think. I could be wrong about that. So I didn't quite get a clear picture, but yeah, it does something fancy that gives you random access. So you get random access iterators. But the nice thing about it is when I add to the front of a vector, of course, I have to, I add to the front of the backing array and everything has to shift, right? So if I add something to the front, I copy every element one spot to the left or to the right. With a double-ended queue, I don't need to do that. I can add very quickly to the front and the back in constant time without shifting and making copies. So you get random access, it's very fast. You also are able to add and remove things from the front very quickly. Yeah, sorry, what's that I said? Better than vector in the middle, worse than list. Yeah, So the middle, you still have to move some stuff around, but at the front and the back, very, very fast. All right, so again, we have the student object. I've implemented the less than operator here, also the equal to. Yeah, so we made a bunch of students. We have an output stream iterator, and then we made a deck of students called studec. I guess the one thing to note is we do declare when we've used the copy constructor, so we can see how many copies are being made. So yeah, the first thing we do, we make our, I guess, 7 students, and then we push 4 of them onto our deck. All right, so when we push the 4 of them on, the copy constructors for those 4 were called, and then we could print them out. So yeah, if we did this with the vector, of course, we would have a lot of copies and destroyed items and things like that. The deck is really sort of quite efficient at that. Then we can push and pop from the front, or, pushed onto the front. We could pop in the back later. Just to show that when we push onto the front, only a single copy is being made again. We're not, we don't have to shift elements over. And let's move this down here. Okay, so pushing and popping. Again, we push these guys onto the front, and only one copy is made for each time we pushed it. So then we have a deck with 7 students, and we have a random access, but we also have that quality that we get with the list, where I only make one copy of the student as long as I'm adding to the front or the back. Yeah, and then we can pop some off. Yeah, that's fine. We don't have to do that. And we get, in this case, we can declare a deck iterator pointed at the beginning of my deck, and then I can use random access. So I can access the student at position 3. Yeah, so student at position 3 is Bob, who's in chemistry with a GPA of 11.9. So yeah, so decks are sort of a nice middle ground between vectors and linked lists. All right, questions on that? All righty. Okay, so we'll talk a little bit about associative containers, although we're not going to show any examples. And then, so yeah, associative containers are containers that use keys. So basically the keys, you use the keys to retrieve the items. Sometimes you use the keys to retrieve the keys themselves. So you check to see if there's an instance of some object in your set. So keys are containers that use keys. The keys are stored in some user specified order. The default is ascending, but you can pass in some function that will order it however you like. We have sets, we have multi-sets. So these are sort of mathematical concepts, right? So a set means no particular, a set means we store things, but there's no duplicates. And a multi-set allows duplicates. And a map is basically a key value pair. So a set only holds a key, the map holds the key value pair. Otherwise, it's the same thing. A map has no duplicates, the multi-map, yes, we're allowed duplicates. And yeah, so this is summed up here in this small little table. So a set stores keys only and does not allow duplicates. The multi-set stores keys only, but does allow duplicates. The map stores key value pairs, similar to the map item that we saw earlier. or we made earlier. Does not allow duplicates. This is no duplicate keys, right? The values can be duplicate. The multi-map key value pairs, and we can have duplicate keys. So there's things like we get some functions: insert, find, lower bound, upper bound, and we get bi-directional iterators on them. So no random access, but we can traverse our set of keys and access the elements that way. All right. So yeah, that's questions on that. You'll see more of this sort of thing in 2402 if you haven't already. Container adapters. So these are essentially high level, similar to what we did. I believe I explained it before, but when we made a stack out of a vector and we used private inheritance to hide all of the vector's functions, and so that we only had pop and push. This is similar, right? There's some, these are high-level containers that provide stack functions or queue functions. And I can, if I like, so by default, they have a default container in the background. I think stack is probably vector by default. Queue might be vector as well, I'm not sure. Queue is probably deck. Regardless, priority queue might be vector. Yes, this one's, I think, vector by default. I'm guessing this is deck. I'd have to look it up. But, similarly, when we declare a stack, we could say, well, a stack of strings. And then we can also provide a second argument saying, well, use a vector as the collection class that is backing my stack class. All right. So, yeah, because basically what we're doing, we don't have any new functionality in a stack or a queue, but you're going to hide some of the functions from these other containers, essentially. Priority queue is a little bit different. It's sort of a min or a max heap, which can be implemented using a vector. So a stack implemented with any sequence container. A queue is implemented with a deck or a list. Yeah, that makes sense. And a priority queue can be implemented with a vector or a deck. Container adapters do not support iterators. All right. Questions on container adapters? All right. STL algorithms. I might have to try and speed up a little bit. So these are global function templates that operate on containers. So we can use iterators. It can also work on non-STL containers such as primitive arrays. You can call a sort, I believe you can, I'd have to look it up. But yes, there are algorithms where you can pass in arrays and pointers and things like that, and it'll do the same thing as if it was some collection class using an iterator. So yeah, and as described before, the iterators provide a layer of abstraction between our containers and our algorithms. So when I call an algorithm, I often use a pair of iterators, and it often will return an iterator in some cases, if I have to find an item, for instance. Algorithms require iterators with specific properties. Yeah, of course, there's, I guess, more algorithms that will run if I have a random access than, if I don't, I guess. So sort, copy, remove, fill, replace, there's a lot of stuff that we can do. So let's take a quick look at some of these examples. So again, we have the good old student class. I have a less than operator for sorting, of course, and I have a double equals. This would be for finding. And what is it? Oh, and I also have an assignment. What did I do here? I don't seem to have an assignment operator. Okay. So we'll hide this for now. Okay, so the less than, we sort by alphabetical order, and the equals is if the two names are equal. So if I want to use a find algorithm, I do need this, this operator by default, or I can define my own. So again, we'll declare some students. We have a vector. We push some students onto the vector. These are objects. And then, yeah, let's say I declare, well, I've included the algorithm library. So now I have access to a sort function. The sort function takes a iterator. So I can say stu vect dot begin. And then I want to sort up to stu vect, yes, dot end. So rather than passing in my vector directly, I take two iterators that, define a range in my vector, and then I call sort on them. And then I can, let's cheat a little bit here. Declare my output stream iterator and print them out. What are you complaining about? Oh, I don't have, for some strange reason, I don't have my iterator. There we go. Okay, so my output stream iterator, and then I can, well, I don't need that. I didn't even use it. All right, so I'm going to print out my vector the old-fashioned way, and it should be sorted by default by the alphabetical order. Oh, yeah. I guess I'll comment those out. But when we print out the students, Amy, Joe, Matilda, Stanley, so we get alphabetical order here. Let's comment this out. Okay, so alphabetical order. So nice. So yeah, basically the same thing, but I need the algorithms class, and then I pass in iterators. So I could have sorted my linked list this way also. But yeah, let's take a look at some others. Let's say I define a function called pass. So Boolean pass, I take a student reference, and I'm going to use poor design here, and I'll say return S1 dot GPA greater than or equal to 6.0. All right, so if you have a GPA of 6.0 or greater, you pass. And then okay, so I have a function that determines if a student will pass, and I'll say, if all of, so this is another algorithm I get from my algorithms library, and then I still need to use iterators to access it. So I'm going to say, well, start at stuvec.begin and end at stuvec.end, and check if these students pass. So if they all pass, then I'll print everyone is passing. Or otherwise, I can print not everyone is passing. Okay, so not everyone is passing. And we could see here that poor Stanley is failing. So if we just went up to 1 before the end, then we're excluding Stanley, and then everybody should be passing. So the first 3 students, everyone is passing. Okay, so that's, one of the things from the algorithms class that we can use. And we define our own sort of predicate, right? So it's just a Boolean function that takes a student as an argument and returns true or false. So yeah, questions on that? Okay, let me copy some of this. I'm going to make another function. All it does is prints the student's GPA. I have to make it a friend. All right. You know what I'm going to do? I'm going to make this a static function. Going to cheat a little bit here. And then I'm just going to, yeah. All right, so I'm using poor design, but I'll put the static function right in the header, and then I can avoid all the headaches that come with having to make it a friend and whatnot. So now I can call on something like this. Sorry, let me see. I lost my place. Oh, yeah, sorry. Okay, so we can print out all the GPAs. I'll say, I was way in the wrong place. All right, so if I wanted to print out everyone's GPAs, I would say for each. And then again, stuvec.begin and stuvec.end. So each of the students in this range, I'm going to apply my student print GPA function. Okay, so yeah, I can iterate. I can do a for each loop using iterators and then supply some function to apply to each of the students within that range. So there are, of course, I could have done this if I have random access. I could have done this just with a for loop. Of course, if I have a linked list, then I don't have random access. So something like this would make a lot more sense. All right. The other thing, I guess, let's say I wanted to find Matilda. So what's going to happen is I want to I could do this. I could look for the object. It's going to apply my overloaded equals function. So to check if 2 students are equal, we just check to see if the names are equal. So in my main, I can find this student if they exist, and it will be assigned to this iterator, and then I could print out. Since I know this student exists, I can print them out. So finding Matilda, the student Matilda gets returned in the iterator, and then yeah. All right. So the other interesting thing you can do is I can say, well, I can overload this equals operator, right? And say, well, instead of trying to find a student object, that's not very useful. Maybe I could say, set it equal to a string. So now in my If I'm trying to find a student by name, then it makes sense to look for a string rather than the object, which I might not have access to. So I can ask, well, does the name of this student equal the name of the argument that I'm giving? So then in my main function, I could say, right, find a student that has this name Matilda. And since I've overloaded this operator, that's what will get used. So yeah, finding Matilda, it still returns the student that's equal to Matilda. And I have full control over, so I can basically supply any object here I like, any criteria, and just overload the equals operator, and it will return something. It will return the student that matches the criteria that I've defined. All right. Yeah. All right. Well, there's a bunch of other ones we can. What else? I'm trying to think of what else is relevant to find a minimum student, I guess. We can try and do that as well. So if I wanted to find the minimum student, by default, of course, it's going to use the less than operator, right? So I can say found equals min element of stuvec.begin and stuvec.end. Or I can define my own function there if I like. So the min student is min by alphabetical order. So by default, my less than operator is alphabetical order. So finding the minimum student is Amy. Do I have some other way to order them? Yeah, if I say, oh no, that's GPA. Okay. So I don't have any other way to order them right now, but I could also define another function and add it here. All right. Questions on that? There's a bunch more I could show you, but I'm going to stop there. I'm kind of, we'll jump back to exceptions. I think that's enough for tutorial 10 though. I've basically shown you. If you don't, so C++ algorithms library, if you Google that, it takes you to the CPP reference. So you can, look up all of the possible things that you can use in your algorithms. So there's a bunch of them. So if I did not show you the thing that you needed here for your assignment, you can definitely find it just by Googling C++ algorithms, and that'll take you there. All righty. The end. So that takes us to the end of the STL library. I'm going to move on, but of course, if you have any questions, just shout them out. So we're going to try and finish exceptions. I'll see, I might have to skip a few of these things. So where we left off is basically talking about the control flow when you throw an exception and how essentially, I start from here. This is my function call stack. I call the function middle. Middle calls divide or divides. In divide, I throw an error. So instead of returning this, I simply pop this off the stack. I pop this off the stack until I find this catch block. So there's, and as a result, this line gets skipped. If I had anything else after divide, then those would get skipped as well. So yeah, throwing an exception can be useful, but what happens when we do it is sort of important. So if we go to P3 and P4, Okay, and this is so the catch catches there before it happens, or does it safely let the catch occur? All right, let's briefly go back to. All right, so this is the original example, just to, I guess, as a reminder. So in my main, I call function one, I embedded in a try block just to, because, you know, there might be somebody throwing an error down there. So in function one, I call function two. In function two, I call function three. And in function three, I throw this error. But for now, let's not throw the error. Let's see the flow of control. So I call function one from main, I call function two from function one, I call function three from function two. Then I'm in function three, I exit, and then I go back down the call stack until I get to main, and then I exit main. So what happens if I throw an error in the middle of function three? Well, I go up the call stack until I reach function three, and then I throw that error. So this line gets skipped, this line gets skipped, this line gets skipped, and this line gets skipped. So control goes all the way back to this catch block, and then this gets executed, and then the flow of the program resumes right after the catch block. So the catch catches the error before it happens, or does it safely let the error occur? Yeah, so the idea is that if the error is, we do some check and there's some error to be run down here, maybe divide by 0. So we throw this so that this does not get run, essentially. That's the plan. So yeah, other questions? All right. Okay, so now, now that we know the control flow is interrupted, we're going to look at some of the consequences of that. So let me actually get a little bit prepared here. Okay. All right, so here we have a main function and we have an enter name function. So we define some string and we, you know, give it a default value of abracadabra. We don't have to do that, but we do in this case just to illustrate some things. We call enter name and assign the return value to some name, and then we print out some name. So here, enter name is quite simple. Declare a string, take the user input, and then return what the user inputted. So then that gets assigned to some name, and we print it out. So easy peasy. Yeah, all right. No, sorry, we're on P2. Nope. And P3, I believe. Eh? Yeah. So enter name, Bob, and then I just print out the name Bob. So what we're going to do is say that, well, maybe if we enter the name Timmy, maybe that's going to cause a problem. So what we're going to do is within the enter name function, I'm going to put a try. I'm going to put a try catch block. I'm going to say, well, if the user enters Timmy, then I'm going to throw an error. I'm going to say, well, I would love to believe that you're Timmy, but Timmy has been eaten by a giant squid, so you're suspect. All right. And then right after the try block, I'm going to have the catch block. So this will get thrown. It will get caught here. It will print out the error, and then we're going to pick up right after the catch block and return S. Now, this is not a value judgment. We're simply showing different Did I not save that? Yeah, we're simply showing what can happen when you do things a certain way. So name one, I say Bob. It says Bob. If I say Timmy, it says Timmy has been eaten by a giant squid. However, we didn't actually skip any of the code. We went to the catch block, we executed that, and then we returned this name. That got assigned to some name, and then we printed it out. Okay, so that's all well and good. We've not really avoided any code. We've simply given a message to the user. So maybe we want to try having the try block up in the main function. So let's look at example 2. No. So here we want to say, we are going to embed this in a try block. So we're going to say, well, some name equals enter name. And if this doesn't throw an error, then we're going to resume this piece of code. If enter name does throw an error, then we're going to land in the catch block, where we print out the error and then we resume control here. And down here, instead of having this embedded in a try catch block, we're simply going to throw the error. So if S is equal to Timmy, we're going to throw this error, and then we'll see sort of the consequences of what happens. All right. Enter a name, well, Bob. So it looks like no trouble here. So I entered the name, it called the enter name function, it returned S. S got assigned to some name. I printed out this line. I skip the catch block, I resume control here and print out Bob. On the other hand, if I tried Timmy, it says help, Timmy's been kidnapped by a giant squid. So a couple things to note. We skip this line here. So because this enter name function throws an error, it does not return to this try block. It returns to the catch block where we print out the error. At which point we resume the function and we print out the name, and this, you can see the name is abracadabra, right? So if we look here, the name that we print out is abracadabra. So what happens is we didn't return from this function. We did not execute this return S statement. So that name never got assigned to some name, right? So yeah. Now this is neither right nor wrong compared to the other way we did it. It's just different. So whatever your needs are, you have to sort of consider how you structure your try and catch blocks, things like that. Yeah. Questions so far? Okay, so finally we can do, what did we want to do here? Yeah. All right, so now number 3, let's say maybe instead of calling my enter name function, I'm going to make a third function. So I'm going to call enter name. I'm going to take this enter name in, but then I'm going to call on a third function to check to see if the name is acceptable. And if it's not acceptable, then in that third function, I'm going to throw the Timmy's been kidnapped by a giant squid error. Okay, so the same thing, we've just introduced a third function. So we call the check name from the enter name after the user has entered the name. And then, yeah, so otherwise, basically the same thing. Do I need a catch here? I do need a catch here. Why don't I have a catch here? Yeah, so this should be embedded in a try catch. Okay, so the same as before, we have a try catch in the main function, calls on enter name, and then enter name calls on check name, which check name might throw an error. So enter name, Bob. So I enter the name. It does not throw an error, so it returns and says even closer call where find two. And then the returns the name Bob, which is assigned to some name, and then says looks like no trouble here. So even closer call where find two, looks like no trouble here. And then we print out the name Bob. If I say run that again, say Timmy, it says help, Timmy's been kidnapped by a giant squid, and again abracadabra. So we went to the check name function, we throw this error, these lines get skipped, this gets popped off the function call stack. We return to the catch function, we did not assign any name, we skipped this line also. We print out the error, and then we print out the name, which is still abracadabra. Okay, so there's just three simple scenarios about control flow when you throw an exception. All right, questions? Does the program crash if you throw with no try? Yes, that's a good question. So if we said, yeah, so we have no try catch. We've simply thrown this. Enter a name, Timmy. It says terminate called after throwing an instance of, constant character array. So yeah, if there's no catch, then the program crashes. Also, maybe we try and catch, let's say we try to catch a string. Well, a string is not the same as a constant character array according to the compiler. So again, this error does not get caught because technically this is a different type. I guess it might make more sense to say, maybe if it was an int, since string and constant character array are kind of close. But yeah, even if I have a try catch block, if I don't catch the right type of error, it'll still crash. Other questions? Okay, I believe, yeah, number 4 as well. So in example 4, we have a barnyard, the good old barnyard harmony, right? So we have our base class of animal. We have a bird, which is a type of animal, a chicken, which is a type of bird, cat is a type of animal, and they all sing. We have the pure virtual sing function in my animal class, which makes animal an abstract class. And then I override that function in each of the derived classes. So the bird says tweet, tweet, chicken, cluck, cluck. Cat says meow, and the pig says oink, oink. All right, so we make 4 animals, we push them onto our vector, and we do the barnyard harmony, and then we destroy them all. So yeah, we're in P4 now. Okay, so our barnyard harmony looks like this. Fantastic. Okay, let's say now, however, pigs don't sing. So when we call this function, we will throw a pigs don't sing error. Okay, so now, where are we? Okay, so now we might throw an error in our barnyard harmony. So we're going to encase it in a try catch block. So the entire thing we will put in this try catch structure. All right, so now if there's an error, we will exit this try block, come to the catch block and say somebody complained about the noise again. No, I don't think I saved it. Okay, so barnyard harmony, we get the chicken. Chicken, little red hen says cluck, cluck. When the pig goes to sing, the pig throws this pigs don't sing error. It gets caught here. and someone complained about the noise again, and then this for loop is abandoned. So we are no longer having the barnyard harmony. As soon as the pig tries to sing, it's over. All right. So that is one possible way to embed this. Maybe we don't want it to end though. Maybe we just want to say, well, you know, whatever the pig tried to sing, somebody complained, but let's keep going. So what we're going to do is we're going to restructure this so that this is, instead of having the for loop inside the try block, we're going to have the try block inside the for loop. Okay, so this entire, we have this for loop, which now has this entire try block and the catch inside of it. Yes, with memory allocated on the heap, the try catch. Yes, exactly right. That's sort of the main point that we're going to get to. All of this other stuff is important, of course, but the main is the memory management. Okay, so now originally when the pig tried to sing, somebody complained and the barnyard harmony was over. So now I put the try catch within the for loop, which means that here, when the pig tries to sing, an error is thrown. It's caught here. We execute this line, but then we resume, control resumes here. The program resumes here, which is still inside the for loop. So we go to the next loop and then we execute it again. And then even though the pig tried to sing, the rest of the barnyard harmony gets to finish. Again, this is not saying that one is better than the other. In some cases, you might want it to execute this way. In some cases, you might want it the original way where, you abandon the for loop when the error happens. But yeah, questions? All right. Yeah, so this is just a little review of what we just saw. So whether I put the try or catch block inside or outside of the for loop affects the behavior. So yeah, we should always think about how this flow of control happens. Okay, so yeah, the throw statement has one parameter. So I can throw at any one time, I can throw one type of error. And the compiler will look for a catch block with a matching parameter. But maybe I have my function calls another function, which calls another function, and there might be multiple types of errors that are going to be thrown somewhere down the call stack. So what we can do is we can put a bunch of catch blocks along with our try block and catch all kinds of different parameters. And yeah, and at the end, if we want to catch anything that is thrown, we can use the ellipses. So these 3 dots mean catch anything that gets thrown. So the drawback of doing that is that I don't have a variable here now, right? I have no access. Because I don't know what I caught, I can't use it. So I can't print out an error message. I can't do any of those things. Or sorry, I can't print out an error message that's contained in the error, right? So if I had an exception E, I can call E.what to return the error, but of course I have no variable. All right, so number 5. Okay, so we again have the same class hierarchy, but now we just have a bunch of empty classes, right? Because we don't really need them to sing or have names or any of those things. We just need to be able to identify them. So then we can declare some objects, a chicken, a cat, and a pig, and then we can ask the user for their input. And then based on their input, we can throw a different animal. It sounds terrible, but yes. So if the user chooses bird, we're going to throw a bird. I'm going to talk a little bit about why we have brackets here and not here in a second. If they choose chicken, we'll throw the chicken. If they choose cat, we'll throw the cat. And if they choose pig, well, we'll try and throw the pig. Otherwise, if all of those things fail, then we're just going to throw whatever. And now I have, this is all within my try block. And now I have multiple catch blocks. So I can catch a chicken. If I catch a chicken, I say chicken alert. If I catch a bird, I say bird alert, cat, pig. And then at the end, I have this catch all. So yeah, so we'll say caught something, don't know what. All right, so nothing to be done. Fantastic. Select my activity. Well, let's throw a pig. It says pig alert. So I typed in pig. It went through here. So yeah, I threw a pig and the pig got caught down at the bottom. And you'll notice that only this line executed. I did not by default run into this catch block. So, you know, and if I said chicken, then it says chicken alert. Again, this is the first element. I skipped the rest of these catch blocks. And then here I could say, let's say, exiting main. Okay. Yeah, so multiple catch blocks for multiple types of errors. Questions on that?
The note says order is important.
Yeah, so there's a couple of things I want to address. So yes, the order is important. So let's say I took this bird catch block and put it in front of the chicken catch block. So what do we expect to happen? So if we look at our class hierarchy, a chicken is a type of bird and a bird is a type of animal. So when the compiler looks at the catch blocks, it starts here and it chooses the first one it can find that matches. So if I throw a chicken, it's going to say, well, is a chicken a bird? Yeah, it is actually. So this is the one I should execute. All right. And the compiler actually will warn you. So exception of type chicken will be caught by the earlier handler for bird. But it's just a warning. So it'll still let you do this. So I can say now, P5, select my activity. If I throw a chicken, it says bird alert, and then it skips the rest and exit main. So this catch block is completely useless now. Yeah. And if I threw, I guess, if I put this at the top, then I'm in real trouble since this will catch everything. Now it's complaining. Handler is masked by the default handler. So this is actually producing an error, whereas the other way just produced a warning. Yeah, so we'll put the chicken before the bird. That way, if I throw a bird, it does not get caught by a chicken because a bird, even though a chicken is a bird is not a chicken. So yeah, then everything gets caught in its correct place. I got to save it. Whoops, whatever. All right, let's say I threw a walrus. Caught something, don't know what, exiting main. So I got caught by the catch-all at the end because it didn't recognize it. All right. So yeah, order is important. The other thing I wanted to briefly touch on. So when we declare an object, we don't declare it with these. If it's a no argument constructor, if I'm calling on the default constructor, I do not put brackets here. There's a reason for that. Although I do put them here. If I did this is C++, man, there's some says type name is not allowed. So here I'm trying to throw a type. Whereas if I include the brackets, it recognizes, oh, call on the default constructor, make a new bird. So it's crazy. Here, this is actually, when the compiler reads this, it thinks that this is, I'm declaring a function called redhen that takes no arguments and returns a chicken. So that is why, because this is ambiguous, if I want to declare an object with no arguments, I leave off the brackets here, although I have to include them here, which seems really weird to me, but that's C++. All right. Questions on this? Okay. So yeah, the order matters, right? So here, if I take a look at this, if I throw a car and look at my class hierarchy, well, a car is a type of vehicle. So this car is going to get caught right here. So by putting my, the top of my hierarchy at the top of my catch list, I'm really, all of these become useless. If I removed this catch block and I throw a car, well then, is a car an aircraft? Nope. Is it a boat? Nope. Is it a Mazda? Well, no. A car is not a Mazda. A Mazda is a car, so we're going to skip that, and we will get caught by the proper catch block here. So the order of the catch blocks, you start with your derived classes. The bottom of your hierarchy has to come first, then your base class, then your catch-all. So I could put vehicle down here, and that would be acceptable. All right. This makes a good exam question, by the way. I think it's on the practice exam as well. So yeah, questions on that? All right. So we can rethrow exceptions. Yeah, I think we'll have enough time to finish all this. Excellent. So we can throw an initial exception. We can catch it here. So here we call on the middle function. The middle function has its own try block. It calls on divides. Divides throws this divided by 0. It gets caught here. We give an error message and then we rethrow it. If we put no parameter, it's going to throw whatever was caught. Yeah, and then we can rethrow it and catch it again here and print out the error again. Let's take a look at that example. All right, so we have our check name. Where am I here? We have a check name, we have our enter name. So we have our, from main, we call enter name. From enter name, we call check name. Check name possibly throws an error. So this we've seen before. So now what we want to do is we want to embed this check name in its own try catch in my middle function here, enter name. So what I'm going to do is replace this with my try catch. I'm going to handle the error here, and then I'm going to rethrow this error. Okay, so what are we in now? P6. So enter a name. If I say Bob, it just prints out Bob. If I say Timmy, well, I throw this error, it handles it here. We can see handling error in enter name. We print out the error, so help, Timmy's been kidnapped by a giant squid. And then we rethrow the error. We go back up to the main function where we can see we've caught it. It says main function says help, Timmy's been kidnapped by a giant squid, which is this line here. And then we resume control and print out the name, which is, of course, abracadabra, because we skipped the return statements. So we can, rethrow the same error. We can also throw a new error. New error from, what is this? get name, enter name. So we don't have to throw this same error we got. We could throw something different. We could throw an integer. We can throw whatever we want, an exception. So enter a name. Let's say we enter Timmy. So we handle the error in enter name, help Timmy's been kidnapped by a giant squid. And then in the main function, we've thrown this new error from enter name, and that gets printed out, and then control resumes here. All right. So rethrowing. Questions on that? Okay. Yeah, so then sort of the main issue here. Oh yeah. The other thing, which we're not going to look at, you can declare what you're allowed to throw. I think I'll skip this. We'll come back to it if we have time. But I can say my function can only throw an int or an exception. Or if I don't have a declaration like we've been doing, then you can throw anything. Or I can put this throw clause with an empty parameter list, which means you cannot throw anything. So that happens if I do. Now, if I do throw something, terminate is called on my program. Actually, we can run that really quickly, I think. Easy enough. So check name will just say throw nothing. And then I have to make sure that this matches. So now this check name function is not allowed to throw anything. However, I do actually throw this error. So if I enter Timmy, terminate gets called after throwing an instance of this. All right. Stack unwinding. Yeah, we got 10 minutes. Perfect. So I'm going to probably skip the first example because it's just sort of dumb. But yeah. So what happens when I pop these stack frames off, when I throw my error and I skip back until I find a catch block? Well, if I have, say, my main, and then I call this function, and then I call this function, and then I call this function, and I have a catch down here, and I throw something up here. Well, the compiler looks for the catch. It pops that stack frame off. All of your local variables are destroyed. Pops that stack frame off because there's no catch. All of those local variables are destroyed. And then pops that one, and then finally lands here and resumes control. So some of the problems, return values are never returned. Memory is not deallocated. Local variables are destroyed though, so that's nice. So yeah, this can, if you throw something and you're not careful, you can end up in some inconsistent state in your program, right? So I've actually written this line in programs and then seen it execute. It's terrible, but it can happen. Oh yeah, so stack unwinding. So one of the ways of graceful stack unwinding, by stack unwinding, we mean handle dynamic memory that you've allocated in an intermediate function. So one of them, put all pointers in the catch parameter. This is, I mean, I'm not even going to bother with this one since we don't have the time. You shouldn't do this, basically. This is just a terrible way to do it. But I could, throw my pointers to my dynamic memory into my error. And then, whoever catches my error is forced to clean it up. Another way to handle it is to put a catch block in every function that might potentially need it. So we saw before, if we had, a bunch of function calls and I threw an error at the top, well, if I have a catch block in every one of these and I delete things all the way down, then, then I've handled my memory. I have no memory leaks. This is, each function does its own cleanup. That's good. And uses good encapsulation. That's also good. The third way, instead of using dynamic memory, or if I want to use dynamic memory, I can encase it in an object. So I make everything an object, and then I can declare it locally. And then inside that object, it declares some dynamic memory. But what happens is the destructors are invoked once we pop that stack off the stack frame, and that memory will get deleted. All right, so let's quickly go through this. Yeah. So this is the first, I'm just going to skip that one. I don't really like that. It's not, you should never ever do this. So there's really no point in going over it. So what happens here is I have a main function. I call this initialize method or function. In my initialize function, I enter a number, which is the number of arguments I'm going to enter. So once I enter that number, it allocates a dynamically allocated array of that size. And then I start entering the elements. So yeah, it assigns, it calls this enter int function, and whatever's returned there gets assigned to this array. And then it prints out the array, and then it deletes it. My enter int function, I read in one integer from the user. I check to see if it's any good, right? So if this is expecting an integer, if I put in let's say a character or a string, this flag will be flipped. So this cn.good will return false. And then if I, invert it, it returns true. So in this case, I'm going to say, well, you've got some bad input. I'm going to throw a bad input error, and then that'll get caught down here. Okay, so that's the basics of it. Let's see. Where am I? P7. Okay, so enter a number of elements, 3, 1, 2, 3. So you entered 1, 2, 3. Fantastic. Okay, so if I use valgrind, 3, A, B, C. Oh, yeah. So I have, I did that. I did not mean to do that. So enter 3 elements, 1, 2, 3. All right. So all heap blocks for free, no leaks are possible because I entered integers. If I enter A, B, C, then I get this bad input error. And now I've lost this because, of course, the error gets thrown from my enter int, which occurs up here. So then this exits. There's no catch block here. So, this gets thrown here. This all gets popped off. All of these lines get skipped, including the delete my array. And then I get caught here. I handle the error and I return 0. So what I want to do here is I want to actually encase that in a try catch block. So I'm going to use my intermediate stage is, I'm going to put this for loop where I possibly throw an error into a try catch block. So I'm going to catch any error it throws. And if some error is thrown, then I'm going to delete this dynamic memory and rethrow the error. Okay, so now, did I not save it? Okay, so 3 elements, 1, 2, 3. I entered 1, 2, 3. All heap blocks were freed. Everything's fine. Now I'm going to enter something bad. So let's say an A. I got this bad input error, but all my memory leaks are gone, right? Because I've caught it and cleaned up my memory and then rethrown the error. All right. Questions on that? Okay. Finally, probably the best way to handle it is to use the destructors. So destructors we don't have a garbage collector like in Java and C++, but destructors are kind of cool. They kind of, if you plan out your code well, using local variables, you can do some interesting things. So instead of using a raw array in my function, I'm going to declare this class called int array. So this int array takes some size. Sorry, I have somebody wants to clean my gutters, I'm sure. So yeah, this takes a size as a argument and then makes a new array of ints of that size. And then in my destructor, I'm going to delete that array. And then I'm going to overload this subscript operator. I don't do any safety checking or anything. I just forward it to my backing array. I return by reference, right? So that I can assign new values to this, to the array. All right, so I have the same structure as before. I call initialize. In my initialize, instead of declaring a raw array, I use my int array object. Right, so I declare one of these. I say enter the elements. I have the same for loop as before. If I enter them all correctly, I print them out. If I make a mistake entering them, I throw this bad input error. There's no catch block here, so this stack frame gets popped off the stack. However, when that happens, since this is statically allocated, statically declared, the destructor is called. And then in the destructor, I delete this dynamic memory. All right, let's, I guess, see it in action, and then we can answer any questions. All right, I should have run val grind, but 1, 2, 3. I entered 1, 2, 3. Say val grind. 3 elements, A, B, C. I get this bad input error. However, all my heap blocks are freed. No leaks are possible. So yes, the error bypassed this function, but the destructor still gets called on this. So yeah, this is basically probably the most important lesson from this is make sure you don't end up with memory leaks because you've thrown an error. But yeah, questions on that? All righty. It's this 416 number, which is always, I don't know, either my taxes, I'm under investigation, or I don't know. All right. So yeah, that's it for this class. Yeah, thanks a lot for hanging out all of these early mornings. The early morning classes are the best. It's all good students in early morning classes. That's a nice thing. You have good students in the other classes as well, but you know, at 8:30, only only the good students are waking up. All right. Thanks a lot for listening. You know, I will of course be in touch. I'll look about setting up an exam review, and I will send out a link to the exam review that I do for the other classes. But otherwise, you know, it's been a real pleasure. Thanks for hanging out, and good luck on the exam. Oh, I guess I should talk about, so I will be on Zoom during the exam. I don't know if I wrote that on the practice exam, but if I didn't, I'll update that. But yeah, so if you have questions, I'll be on Zoom. You can also email me. Try and stay off Discord. But yeah, that's it.